again, at some point in your life, you've probably heard the saying, correlation does not imply causation. So in this video, we're going to talk a little bit more about what that might mean. We're going to have a little bit of fun over here. We're going to consider some examples of quantities that could be highly correlated. However, while this might be fun in the moment, it's also a little bit of a warning for us to not infer causation based solely on correlation. And also, it tells us a little bit about why it's important to establish some intuition around confounding variables before claiming a true causal relationship between two variables. Hi, in this video, we're going to talk about correlation and causation, specifically whether two variables that are correlated is necessarily indicative of a causal relationship between them. So the question we were trying to ask is, if we have two variables x and y, and they are correlated, can we expect to see a change in y if we change variable x? This is true in some cases, and we can think of a trivial example over here. So say we're talking about a clinical trial for a drug, and the variable x is either 0 for no drug and 1 for the patient was being given a drug. And y is some variable indicative of the health of the patient. It could be blood pressure, it could be, what do we call it? Outcomes in terms of longevity, whatever. So let's call it health of patient. And let's assume that the drug does actually work, right? It's been verified to work. So in this case, if we were to change the variable x for a given patient from 0 to 1, we would expect to see a change in variable y. That is, we have the health of the patient improve as a result of having taken the drug. But this doesn't necessarily always hold. This only holds if there is a causal relationship between x and y. And on the next few slides, we're going to have a little bit of fun. We're going to see some examples of cases where two completely seemingly unrelated variables have a correlation, but that clearly does not imply that one of those variables causes a change in the other. So over here in this particular chart, we're looking at numbers of ice cream sales versus shark attacks. And if we look at this, this is something we picked up online. The ice cream sales over the course of a year are very heavily correlated with shark attacks, right? When it goes up, it goes up. Granted, this is not a linear relationship, but even then, we can take this as indicative of the larger point we're trying to make. So we see from January until June, both ice cream sales and shark attacks tend to increase. And then between June and the end of the year, in December, they both drop pretty sharply. And they seem very highly correlated. Now, is it true? Is it true that we can say ice cream sales are more likely to lead to shark attacks? Like, what I mean is an increase in ice cream sales is more likely to result in shark attacks. And on the face of it, that seems pretty absurd, right? And the more logical explanation is that there is something that affects both of these variables in a similar way. In this case, what that would be is probably something like the weather. We're talking about the weather. What happens is in warmer weather, you're more likely to have ice cream sales. And you're also more likely to go in the water. And as a result of that, you have more shark attacks. So in this case, that's the more logical explanation. It's more logical that one variable causes the other, or rather, sorry, it's more logical that there is a single variable that has an effect on both ice cream sales and shark attacks, and not that ice cream sales by themselves are directly like causal or predictive of shark attacks. So that's one example. And we have another one over here talking about high school graduates and pizza consumption. And we've seen over the course of time, over the last almost half a century, since, I mean, I guess it's probably closer to 60 years at this point, we see that the number of high school graduates increases and the number of pizzas that have been purchased also increases. So does this necessarily mean that graduating high school causes more people to eat pizza? Quite clearly not. That kind of does not make sense at all. And what actually makes more sense, what is more likely in this case, is that we have a variable, in this case population, which affects both of these. We have a higher population now than we did 60 years ago. So as a result of that, we have more high school graduates, and we also have more people eating pizza. So that's the more reasonable explanation over here. And again, just an illustration that two variables being correlated with each other does not necessarily mean that there is a link between the two of them. This link does not exist, or does not necessarily exist. And so when we're kind of looking at this as a whole, when we analyze two different variables that are correlated with each other, what is important is to not look at them in a silo, not look at them in isolation. We want to look for the presence of other variables that might influence both of them. And these are variables that we call confounding variables. And it's been said many times, it's very cliche at this point, but I'm going to say it again, correlation does not always mean causation. Thank you. See you in the next video.